Hi guys, and welcome to your last lesson in Unit 4. Today we're going to talk about salt hydrolysis. So we're going to talk about how certain ions in a salt, which is just another word for an ionic compound, how they can hydrolyze or react with water to form acidic or basic solutions. So just to kind of review for a second, another term for an acid-base reaction is a neutralization reaction, because an acid-base reaction forms a salt. So remember, salt is just another word for an ionic compound. Okay, so we in normal terms think of salt as like sodium chloride, like table salt, but in chemistry, the word salt is just another word for an ionic compound. So an acid and a base, so obviously this is an acid and a base, it's going to make a salt and water. And so up until this point in your science career, this product was neutral. And so it made sense that it's called a neutralization reaction. The acid and the base that don't have neutral pHs react together to form something with a neutral pH. However, in this case, it is neutral, but it isn't always neutral. Salts can be neutral, like in the case of sodium chloride, but they can also be acidic or basic. And if they are acidic or basic, then they can hydrolyze with water to create hydronium if it's an acidic salt, or hydroxide if it's a basic salt. So as we saw in the previous slide, so an acid and a base make a salt and water. So salts can be formed from 4 different combinations of acids and bases. So sometimes we call this the parent acid and the parent base. So we can think of it like the parent acid and the parent base come together to make the little baby salt. Okay, so this could be a strong acid and a strong base. It could be a strong acid and a weak base, a weak acid and a strong base, and then a weak acid and a weak base. So those are our kind of 4 combinations to create a resulting salt. And depending on what this combination is, that's going to dictate whether this salt is acidic, basic, or neutral. And so we're going to go through those 4 different combinations, and then I'm going to talk to you about how, given a salt, we kind of work backwards to determine if it's acidic, basic, or neutral. So if we combine a strong acid with a strong base, so we've seen this chart before in a previous lesson. So our strongest acids are up at the top left, our strongest bases are at the bottom right. So then the conjugates are weaker than water. If you remember in that lesson, I used that phrase, the conjugate of a strong acid is weaker than water, and the conjugate of a strong base is weaker than water. The reason I use that term, weaker than water, is because it means it cannot hydrolyze with water. So if you look at the actual terminology used on this chart, here's my strong acid top left. On the right, the conjugates say do not undergo base ionization in water. And if you look at the bottom left, these are the conjugates of strong bases, do not undergo acid ionization in water. So because of that fact, when we have a salt that is the conjugate of a strong base and a strong acid, it is neutral because neither of the ions can hydrolyze with water. Okay, so I have a list of examples. There's definitely more, okay? But if we look for the one that I broke down here, KCl, the potassium would come from potassium hydroxide. The chlorine would come from hydrochloric acid. Both of those are strong, so that makes KCl neutral. This time we are combining a strong acid with a weak base, okay? So if I have a strong acid, just like before, the conjugate of that strong acid does not undergo base ionization in water. But now this time we have a weak base. So the conjugate of a weak base is stronger than water, meaning it can hydrolyze with water. And what is the conjugate of a base? It's an acid. And so that's going to make that salt slightly acidic. Okay, so let's look at this example. So we have ammonium chloride. So ammonium came from NH3, which is a weak base. Chlorine came from hydrochloric acid, which is a strong acid. So chlorine is neutral. It can't hydrolyze with water. However, ammonia can. And when it does, it's going to create hydronium, which is what makes this slightly acidic. Okay? So if we were working a problem with ammonium chloride, we would pick ammonium as the one to hydrolyze with water. And if we were given the Kb of ammonia, we could calculate Ka using our relationship of Kw equals Ka times Kb. So now let's swap it. Let's say we have a weak acid with a strong base. So now, just like before, the conjugate of a strong base is an acid that is weaker than water. It does not undergo acid ionization, okay? But if I have the conjugate of a weak acid, it can hydrolyze with water. What is the conjugate of an acid? It's a base. So if it's hydrolyzing with water, it's creating hydroxide. So that makes that salt slightly basic. So let's look at this example, sodium acetate. Sodium came from sodium hydroxide. That's a strong base. So sodium isn't going to do anything. It's neutral. Acetate comes from acetic acid, which is a weak acid. So that means that acetate can hydrolyze with water, forming hydroxide, which is what makes it basic. Okay? So again, let's say we were given Ka for acetic acid, we could calculate the Kb of acetate with our Kw relationship. Very last combination is the most interesting because we've got a weak acid and a weak base. And so the answer to that is it depends, okay? Because of the fact that the conjugate of a weak acid is stronger than water and the conjugate of a weak base is stronger than water. So both of them can potentially hydrolyze. So here we have to compare their K values. If their K values are equal, then neither of them is stronger than the other, and so it's going to be neutral. If the Ka is greater, then it's going to be acidic, and if the Kb is greater, then it's going to be basic, okay? Now, when we do calculations with salts, you're going to not have weak acid, weak base combination. The only time you're going to see a weak acid, weak base combination salt is when maybe you were given the Ka and Kb and asked to determine if it's acidic or basic. Okay, so let's kind of talk about how, given a salt, we can work backwards to determine if it's acidic, basic, or neutral, okay? So earlier we talked about an acid and a base create a salt and water, okay? So if we think of an acid like HX, X can be any anion. And we think of a base as BOH. So the base is whatever cation, the B, and then with hydroxide. So when those combine, it makes the salt BX, and then it is this hydrogen and this hydroxide that together make HOH, which is water. We just write it as H2O, right? So if we work backwards, then HOH plus this salt makes HX and BOH. So this is just generic, okay? So remember I talked about we call this the parent acid and the parent base to make the little baby salt. So to work backwards, you can think of this like, okay, this cation had to come from my base. So whatever this cation is, just add it to hydroxide to know what the base, the parent base was. And whatever this anion is had to come from the acid. So just add the anion to hydrogen in order to write the formula for the acid. Okay? So the way that I like to work problems like this, so let's say I gave you NaCl. That was like one earlier. Okay? I'm going to break it apart into Na plus and Cl minus. So that's my cation and my anion. So I add the cation to hydroxide to make the parent base. I add the anion to hydrogen to make the parent acid. Okay, so these are the parents to this salt. Now my question is, are the parents strong or weak? Okay, sodium hydroxide is definitely strong. So that means that this is neutral. HCl is definitely strong. So that means that this is neutral. So this salt is neutral. I X'd it out in the sense of it can't react with water. All right. So let's do one more example. Let's say I gave you the salt LiF. So now I'm going to break that apart to lithium and fluorine. So lithium would have come from lithium hydroxide. Fluorine would have come from HF, hydrofluoric acid. Lithium hydroxide, definitely a strong base. So that means that this cannot hydrolyze with water. But HF, it's a tricky one, but remember HF is a weak acid. So that means that its conjugate base is stronger than water. And so that makes this whole salt basic, because this fluorine, being stronger than water, will be able to take a hydrogen from water, which creates hydroxide, which is what makes it basic. Okay. So we're going to determine if these salts are neutral, acidic, or basic. So our first step is to break them apart. So I have potassium and carbonate. Now I technically have two potassiums, but what does the potassium come from? Potassium hydroxide. What does the carbonate come from? Carbonic acid. Now I have to ask myself, are these strong or weak? Well, potassium hydroxide is definitely a strong base. Carbonic acid is not one of my strong acids, so it is a weak acid. So that means that potassium, because it came from a strong base, is neutral. It can't hydrolyze with water. But carbonate, because it came from a weak acid, it itself is basic. So this is a basic salt. All right. Next one, break it apart. Again, we've got potassium, and then we have the ClO4. Is it hyperchlorate? Bad chemistry teacher. Bad chemistry teacher. Perchlorate. Okay. Sorry. All right. So perchlorate. So perchloric acid. All right. Whew, goodness. All right. So this came from potassium hydroxide, and this came from perchloric acid. All right. So this is a strong base. Perchloric acid is a strong acid. So that means that this is neutral and this is neutral, and so this whole salt is neutral. All right, ammonium bromide. So we're going to break that apart, NH4 plus and Br minus. Now, when we see something with this like ammonia or like a N and hydrogen combination, it's not just a metal. So it's not one of our like cation metals that we put with hydroxide, but you should recognize that ammonium is the conjugate acid of ammonia. So that's just when you've got to recognize that you're not going to tack that onto a hydroxide. It's not the conjugate of ammonium hydroxide. It's the conjugate of ammonia. Okay, so you just got to recognize that. And then bromine would come from HBr. Okay, so ammonia we know is a weak base. Hydrobromic acid we know is a strong acid. So that means that this itself is acidic, but this is neutral since it came from a strong. So that makes this salt acidic. Last one, we've got potassium and then bicarbonate. Whoops. So then this came from KOH. This came from bicarbonic acid. So this is a strong base, potassium hydroxide, but this is a weak acid. This is not on our strong acid list. So that means that this one is neutral, but this one is basic, and so that makes this whole salt basic. So remember, if it comes from a weak acid, weak base combination, you would have to be given K values in order to determine it. So unless you are, you're not going to be asked to determine if a salt is acidic, basic, or neutral if it comes from two weak parents, okay? So in all of these combinations, you see that at least one of them is strong. And so it's the parent that was weak that creates the conjugate that can hydrolyze with water and determines the acidity or basicity of the salt. Of course, then when both of them were strong, it was neutral. Okay, so we're going to work a problem. These problems are exactly like the other ones that we used to work. The only difference is instead of being given something that is outright an acid or a base, we're now given a salt. So we have to determine if that salt is acidic or basic, meaning which ion is going to hydrolyze from water or with water. So if I look at this salt, I break it up into its ions. Now, this is another example of a cation that did not come from a hydroxide base. It comes from this base right here. And you see that because it's part of the problem. It gives you that base because it gives you the Kb value. And it's easy to see that this is the conjugate acid. So this is a weak base, so that means that this is an acidic ion. Chlorine comes from HCl, which is a strong acid, so it's neutral. So this salt is acidic, and so this ion is going to hydrolyze with water to form the base and hydronium. Okay, so all I did is I took the ion that is stronger than water. Because it is the conjugate acid of a weak base, it's going to be acidic, so it formed hydronium. So now I'm going to set up my ice chart. 0.5 molar, 0, and 0. I'm not doing anything with chlorine, y'all, because it's just a spectator. It's neutral. It's just going to hang out in solution. Okay, so now I have x squared over 0.5, because I can ignore the change in x. Now, here's where the difference comes in. I am given the Kb of this base, right? Well, it is not the base reaction that I'm dealing with. It's the acid reaction. So this is where I had talked about on the slide where we were talking about when we combine a weak base with a strong acid, we have to calculate the Ka from this relationship. So 1 times 10 to the negative 14 equals Ka times 4.38 times 10 to the negative 4. And if I knock 15 things down on my desk while I grab my calculator. And that means that KB is equal to 2.28 times 10 to the negative 11. Oh, Ka, not KB, I'm sorry. So I had to calculate Ka first. Now I can set this equal to Ka. So then I get that x equals 3.38 times 10 to the negative 6. Take the negative log of that. And I get that the pH equals 5.47, which is an acidic pH, which is what I would expect since this is acidic. All right, let's do one more example. So what's the pH of sodium fluoride? So sodium fluoride breaks down into sodium and fluorine. Sodium came from sodium hydroxide, fluorine came from hydrofluoric acid. Sodium hydroxide is a strong base, so sodium is neutral. Hydrofluoric acid is a weak acid. They love to ask you about the fluorine ion because it's one of the only halogens that's not from a strong acid. So then this itself is basic. You can also be clued in that it's the fluorine ion that's going to hydrolyze with water because you're given the Ka of HF. All right, so I'm going to write my hydrolysis reaction. The fluorine is going to hydrolyze with water to form HF and hydroxide. So my initial concentration is 0.3 minus x plus x plus x minus x, x, and x. So now I have x squared over 0.3. But now, y'all, this is a base, so this reaction is Kb. Well, I'm given Ka. So I have to use my relationship of Ka times Kb equals Kw in order to calculate Kb. Kb equals 1.39 times 10 to the negative 11. So now I can set this equal to Kb. When I solve for x, I get 2.04 times 10 to the negative 6. When I take the negative log of that, remember, y'all, it's POH because this is a base. And I get that the POH equals 5.69. Now, it should clue you in if you tried to tell me that was the pH, that's acidic, and this is a base, so that's not right. So in order to do pH, I have to do 14 minus, which gives me the pH of 8.31, which is a basic pH, which is what we would expect. Okay, so just a few more things, just a few other compounds that can have acidic or basic characteristics. So highly charged metal ions, meaning they have charges greater than +2. Many of these are transition metals. They can form a hydrated complex that will then allow them to donate a hydrogen. Now, you do not need to be able to write these reactions or anything like that. You would just need to recognize that because this is a highly charged transition metal, if you were asked if it was acidic or basic, you would say that it is acidic. But like I said, you do not have to be able to write those equations. We also have oxides. Covalent oxides are acidic because when they combine with water, so they're acidic when they're combined with water. When they combine with water, they form the acid. So they take the hydrogens and they form the acid. Ionic oxides are basic because when they combine with water, they form hydroxides, okay? So just kind of a memorization piece. If you were ever asked, okay, if I put sulfur trioxide into water, you would need to be able to say it's acidic. If I put a metal with oxygen, so calcium oxide with water, you would need to know that it's basic. Last but not least, we have polyprotic acids. You're not going to have to do any type of calculation with a polyprotic acid. You just need to be aware of a couple things. So, of course, monoprotic, meaning that there is one acidic hydrogen. So, one hydrogen per molecule. Di means that there are two hydrogens. And tri means that there are three hydrogens. What you do need to be aware of with polyprotic acids is two main concepts. Number one, they lose one hydrogen at a time. So they lose it in steps. So a diprotic loses it 2 steps, triprotic 3 steps. The second main point you need to know about polyprotic acid is that each hydrogen step has a different K value that gets smaller. So, even though H2SO4 is a strong acid, so you see here that that first hydrogen has a very large K value, the second hydrogen for HSO4 has a smaller K value. Same down here for phosphoric acid. You notice that as each hydrogen is removed, the subsequent K value gets smaller and smaller. So each step is more and more reactant favored. So you can think of it that way. Each step is more and more reactant favored. All right, I did another one under 30 minutes, guys. And this is it for Unit 4.